Okay, calculus fans, welcome back. This is the section we've all been waiting for, and this is when we're really going to tie together the ideas of differentiation and integration, which, as you'll see, are essentially inverse operations. Our work up to this point has shown that if we have a positive valued function, f of x, over the interval ab, continuous over the interval ab, then when we talk about its area, we've shown that its area from A to B is equal to the limit as n approaches infinity of the sum, k goes from 1 to n, of f of any value in the interval times the length of that little baby interval. So adding up, essentially, this is simply the area of a rectangle. We add up n of them, and then we let n go to infinity. And if you remember, 2 sections ago, we actually used this very clumsy expression to compute the area. And the area that we computed at that point, I believe, was this. And later on, we'll see how much easier it is to compute this now. Okay, so the big deal, and this is what we've been leading up to, is how to find the integral from a to b of f of x dx. In other words, how do we find the area under this curve in a nice and easy way? So it turns out that we're going to define a function f, capital F, as the integral from a to x of f of t dt. And, a picture will help here, so just a simple little picture. Here's a graph of f. Here is a, which is fixed. Here is x, which moves. And so big F of x is that. And what should be obvious to you as x gets bigger and bigger, f of x gets bigger and bigger. As x approaches a, f of x gets smaller and smaller. And in fact, big F of a will be 0. And so the objective here is, although we can't really get an expression for big F of x, it turns out we can find the derivative of big F, and that is a big deal. Okay, so that's what's going to happen next. Stand by. Okay, so here's the weird thing again. We're not going to be able to find big F quite yet, but we are going to be able to find its derivative. So here's how that works, and this is a very important proof. We're going to take the derivative with respect to x of big F of x. And by the definition of derivative, this is going to equal the limit as h goes to 0 of big F of x plus h minus big F of x all over h. So that's our standard derivative. And we'll simplify that to be the limit as h approaches 0 of what big F is. So it's the area from a to x plus h of f of t dt minus the area from a to x of f of t dt all over h. So let me just draw a little picture down here. Let's see if this helps. Here's a, here's x plus h, here's my function. Here is the area from a to x. Here is the area from a to x plus h. Okay, so take a look here. If we take the area from A to x plus h, which is all of this, and we subtract the area from A to x, which is this, can you see what we're left with? We're just left with this. And so this is equal to the limit as h goes to 0 of the area from x to x plus h of f of t dt all over h. Now take a look at that. H is the length of the interval from x to x plus h. This on the top is the area under the curve from x to x plus h, and we're dividing it by h. Does this sound just a little bit familiar? So this is equal to, by the mean value theorem of definite integrals, what it's equal to is the limit as h goes to 0 of f of c, where c is somewhere in the interval x to x plus h. Remember that? So in other words, if we just try to change colors here for emphasis, c is somewhere in here. Now, let's take a look at this expression that we have. As h goes to 0, that means this point right here, is getting, well, it means x plus h is approaching x. So this is what's happening as h goes to 0. C is in between here. So as h goes to 0, it's pushing c closer and closer to x. And what that means is that this limit is equal to f of x. And that, my friends, is one of those big deals. So let's summarize what we've learned. We defined big F of x to be the integral from a to x of f of t dt. And we showed that f prime of x is equal to f of x. Pretty cool stuff. Now remember, what we're looking to do is find out how to evaluate this. So here's what we've learned. We've learned that its derivative, the derivative of this expression, is equal to f of x. So let's just pause here for a second. This piece right here is what we call, and let's write it out. This is called an area function. And what this is telling us is that the way the area function is changing is exactly equal to what f of x is equal to. Which makes sense. The bigger that f of x is, the bigger the area is changing. The smaller f of x is, the less the area is changing. So now we get into the idea of antiderivatives. And if the derivative of this thing is f of x, then what that means is that this thing that we're hopefully going to get very close to very soon will be written as big F of x, where big F is an antiderivative of little f. Right? The derivative of big F is equal to little f. So if I take the derivative of this, I get f of x. So this is saying exactly what this says in an inverse way. So, big deal so far. And I left something out, because what I left out is a big part of this. This integral is equal to big F of x plus a constant. And that constant can be any number. And so what I do now is I let x equal a. And if I let x equal a, I get the integral from a to a of f of t dt is equal to f of A plus C, which implies that 0 is equal to f of A plus C, which implies that f of A equals C is equal to minus f of A. That's what I want to write. So putting those ideas together, what I've shown is that the area under this curve from A to x is equal to f of x minus f of A. And so we're just about done, because now what we can write is the area under a curve on a closed interval from A to B, I can write x now because x is out of the picture, is equal to big F of B minus big F of A, which we usually write like this: big F of x evaluated from A to B. Just shorthand notation. And that, my friends, is the way that we compute an antiderivative, or a definite integral, and how we find an area. So we'll summarize this in the fundamental theorem of calculus, and then we'll look at some examples. So we've actually proven the fundamental theorem of calculus, but here we summarize it. And there's two parts. The first part simply says that the derivative with respect to x of the definite integral from A to x of f of t dt is equal to little f of x. The second part, which is what we use to find areas, tells us that the definite integral from A to B of f of x dx is equal to big F of B minus big F of A, under the condition that the derivative of big F is equal to little f. And that's it. That's the fundamental theorem of calculus. And hopefully the title of that suggests that it's pretty important. Probably the most important theorem in all of calculus. And please notice, will you, that this is what relates the idea of differentiation and anti-differentiation, or integration. Okay, so here we go. And as promised, we're going to once again revisit the definite integral from 1 to 3 of x squared. And remember, we did this by hand, by cumbersome hand, in section 6.2. We talked about how we would use our calculator to compute this in section 6.3. And now we see how we use the fundamental theorem of calculus to compute it. And so the fundamental theorem of calculus tells us that this integral, very simply, is just equal to the antiderivative of x squared, which is 1/3 x cubed. And we evaluate it from 1 to 3. And so that equals 1/3 times 3 cubed minus 1/3 times 1 cubed, which is 9 minus 1/3, which is 26 over 3. And hopefully that seems like a familiar number to you at this point. So there you go. That's our first example of how we use the fundamental theorem of calculus to compute the area under a curve. A lot simpler than we did 2 sections ago. All right, here's another example that's going to yield a fairly surprising result. So we want to find the area under the curve sine of x from 0 to pi. That's sometimes described as the area under one arch of sine of x. So we're going to use again the fundamental theorem of calculus, and what we have is the integral from 0 to pi of sine of x dx is equal to, this always takes students a little bit longer to get than other things, but we're asking what is the function whose derivative is sine. Now we know the derivative of cosine is minus sine, so the function whose derivative is positive sine is minus cosine. And we evaluate this from 0 to pi. And so what this gives us is minus the cosine of pi minus the cosine of 0. We really have to attend to our SIGNs here. And so this is minus minus 1 minus minus 1, which comes out to equal 2. Now, to me, I'm always surprised by the fact that the area under a function like sine of x, from 0 to pi, which is an irrational number, comes out to be 2. Always a really cool result. Very surprising. So let's look now at a more general type of example, and in so doing we'll examine and we'll derive Leibnitz rule. So what we're looking at here is to take the derivative of a really complicated function, where the lower limit is some function of x, and the upper limit is some function of x. So the only tool that we have to use right here is the fundamental theorem of calculus. And so this equals the derivative with respect to x of, okay, so what does that equal? The fundamental theorem of calculus tells us it's equal to f of v of x minus f of u of x, where we have the relationship that f prime is big F prime is equal to little f. So, by the chain rule, we have f of v of x, because the derivative of big F is little f, times v prime of x minus f of u of x times u prime of x. And this is known as Leibniz rule, and it pops up from time to time. So let's see, let me give you an example here, and hopefully I can squeeze it in so that you can see it on this same page. So we want to take the derivative with respect to x of the integral, let's say from x squared to e to the x of sine of t dt. So this is equal to, by Leibniz rule, the sine of e to the x times the derivative of e to the x minus the sine of x squared times the derivative of x squared. And that's how we take the derivative of a more complicated looking expression. Okay, a little bit more to go. Hang in there. Okay, this will be our last example. And here what we're asked to do is find the area under the curve y equals 4 minus x squared and above the x-axis. So that means this shaded region right here. And again, the fundamental theorem of calculus tells us that this area is equal to the integral from minus 2 to 2 of 4 minus x squared dx. So I'm looking for an antiderivative of 4 minus x squared, and that's going to be 4x minus 1/3 x cubed, and I evaluate from minus 2 to 2. So that gives me 4 times 2 minus 1/3 times 2 cubed. Got to be really careful with minus signs and parentheses. We get 4 times minus 2 minus 1/3 times minus 2 cubed. So I think I've written that carefully. And if you do your work slowly and simply, you're going to get 16 minus 16 over 3. Check it out. And that reduces 32 over 3. So there's a problem, a little bit more interesting than the previous ones that we have done. So before we conclude, let me just make this statement. You'll notice many times in this particular section that the book makes reference to an idea called NINT. And NINT stands for numerical integration. And this is what you need to use if you don't have a CAS handheld or a computer that can do this work. We are all using the Inspire CAS. And so we don't need to use a numerical integrator, which basically gives you a close approximation to the integral. Our calculators can actually compute exactly the antiderivatives, a definite integral. So the best advice I can give you is just kind of ignore any references that you see in the textbook to Ni and T. So this concludes probably one of the most important sections in the entire textbook. The fundamental theorem of calculus is as important as its name suggests, and at the risk of beating a dead horse, it is the theorem which relates the concepts of differentiation and integration in one statement. So, pretty important. All right, that's it. See you next time. Good job hanging in.